Good day, ladies and gentlemen. We are still talking about the Gibbs free energy in this lesson. I think even during the last two previous lessons, we are also talking about Gibbs free energy. So for this lesson, we basically want to summarize everything that we've been saying about the Gibbs free energy. Because in the next chapter, we are going to talk about the phase change of different materials. So what is the Gibbs free energy, or how to calculate the Gibbs free energy? I think you'll remember that I said that when we talk about the Gibbs free energy, we are basically referring to a situation or equation that can be able to relate the enthalpy of the system together with the entropy of the system. So this equation, it is given by delta G is equals to delta H minus Ts. So all the quantities in the above equations, they refer to the system. So when we have the system, people, we can have different types of the system. Okay, some of the system you'll find that the temperature is constant. But for some systems, you'll find that the temperature is not constant. But for today, I want us to talk about the system whereby the temperature is constant. For a constant temperature process, to calculate the change in the Gibbs free energy, that is being represented by delta G. Delta G will be equals to delta H for the system minus T delta S for the system. Let us not forget that the value H, the capital letter H, it represents the enthalpy of the system, whereas delta S, it represents the entropy of the system. Okay, from this equation, we can be able to calculate the Gibbs free energy of the system. If the question says calculate the Gibbs free energy of the system, it means we have to utilize this equation. But this equation, it can only be utilized when we know the value of H and we also know the value of S at constant temperature. This is not the only equation that can be used to calculate the Gibbs free energy, but it's the equation that is commonly used. So there are a number of things that we can conclude also about this equation. Like for example, if delta G is negative or the value of G is less than 0, it means that the reaction will be spontaneous. But if delta G is positive or is greater than 0, it means the reaction, it is not spontaneous. Okay, similar to the value of K, like we did in the previous lecture, the value of G is a very important factor that can determine the spontaneity of the reaction. Let us not forget, just take note of this thing. If delta G is less than 0, spontaneous. But if delta G is greater than 0, it means that our reaction, it is not spontaneous. But even if the reaction is not spontaneous, it does not necessarily mean the reaction will not happen. There are a number of factors that we spoke about during the previous lecture that can assist the reaction to reach completion. You remember that we spoke about like the catalyst. We also spoke about like the influence of like temperature and even the influence of pressure. Okay, from the previous slide, we said that the Gibbs free energy at the constant temperature process, delta G, it is given by delta H minus T delta S. We can have three instances or three different values, like when you calculate the value of G. There are certain calculations whereby after calculating maybe as for a certain reaction, the value of G will be less than 0. We can also have certain reactions whereby the value of G will be greater than 0. And lastly, we can also have the equations whereby the value of G will be equals to 0. Greater than 0, less than 0, and equals to 0. So those three things, they should be able to give us different meanings. If it is less than 0, it means the reaction is spontaneous in the forward direction. But if it is greater than 0, it means the reaction is non-spontaneous as written. Remember in the previous slide. However, so even if it is non-spontaneous, it simply says that the reaction is spontaneous in the reverse direction. The last instance is whereby the value of G is equals to 0. When the value of G is equals to 0, we normally say that the reaction it is at equilibrium. Okay, moving on, still talking about the Gibbs free energy. We also have what we call the standard free energy of reaction, which is the free energy change for a reaction where it occurs under the standard state equations. So this part, it's more or less the same as the previous part, because even for this part, we are going to learn a different way of calculating the Gibbs free energy. Just that for in this part, we need to know our materials in their standard state equation. Okay, for a hypothetical equation, like we have A plus B, and the product is C plus D. So when we look at this equation, one thing that is important is that we also have the coefficients. Coefficients are very important. From mathematics, we know that like when you balance, everything should balance. Even when we balance the coefficients, they are very, very important. Like the coefficient of A is smaller a. The coefficient of the capital B is smaller b. The coefficient of capital C is smaller c. And the coefficient of capital D is smaller d. So if you want to calculate the Gibbs free energy, if you are given all the materials, the reactant and the product in their standard state equations, or if we know their standard state conditions, it means we can use this equation to calculate the Gibbs free energy. And the equation, it simply says that, I think it's the sum of the product minus the sum of the reactants. That will give us the answer. For example, let's say that, like for A, we know that A is carbon dioxide. I'm just making an example. B, let's say, is water, or C is methane, or whatever. It means that there is normally a table. From your textbook, the table is in 7.2. You go to the table, you look at the values of the standard state condition for this thing, and you simply come and enter these values here, and boom, you can be able to calculate your answer. For example, let's look at different substances, their standard Gibbs energy formation at 298.15 Kelvin. Like for ammonia, the standard Gibbs formation of ammonia is minus 16.45. Carbon dioxide, we have minus 394.36. For dinitrogen tetroxide, plus 97.89. And the list goes on and on. So when you look at like other products like liquids and the solids, so these values, they differ. Like for benzene, the value for benzene is positive 1.24.3. Silver chloride for the solid is minus 0.109.79. So this table 7.2, you don't have to cram this particular table. All you have to do is to know how to use these values. So if you can be given a simple question, say calculate maybe the Gibbs free energy. If you don't have the enthalpy, if you are given the equation, you don't have the enthalpy, you also don't have the entropy, it means that you are simply going to utilize this equation to calculate the Gibbs free energy. And to utilize this equation, it means that you need to know that table 7.2. So it is there in your textbook. So if you are writing a test, always you'll be provided with these values. So let's look at the relationship between the Gibbs energy as well as the equilibrium constant. Equilibrium constant K. I think we know how to calculate the equilibrium constant. But in the next slide, I'll remind you how to calculate the equilibrium constant. But before we can even talk about the relationship between the two. Let's look at a reaction. For an endothermic reaction, for us to have the Gibbs free energy be less than 0, it means that the entropy of that system, it must be greater than 0. For us to have the Gibbs free energy be less than 0, it means that the entropy, it must be greater than 0. So if it is greater than 0, it means that the temperature must be enough for its temperature change in entropy to be greater than the enthalpy. So what I'm trying to say, good people, remember that the value of G, it can also be, it can be at equilibrium. If the value of G, it is at equilibrium, it means the value of G is equals to 0. So where the Gibbs free energy is equals to 0, it means that delta H minus T delta S will be equals to 0. So if it is equals to 0, it means that from that equation, one can be able to calculate the value of T by using that equation, whereby T, it becomes change in enthalpy divided by the change in entropy. If you are given a question, from that question, you are told that the Gibbs free energy is equals to 0, or you are told that we are at equilibrium. So if we are at equilibrium, we know that the value of G will be equals to 0. It means that the G, we can take it out from the equation. And after taking it out from the equation, we can relate the remaining parameters. So from T is equals to delta H divided by delta S, we can be able to calculate delta H. We can calculate delta S if you know the other two. And we can also calculate T which is in temperature. And for this temperature, it is in Kelvins, not degrees Celsius. So if you are given the temperature in degrees Celsius, we first have to convert it into the Kelvins. Okay, moving forward, I want us to briefly look at this slide. So in most reactions, we normally say the magnitude of K is a qualitative indicator. So in other words, so if the value of K it is greater than 1, if it is greater than 1, it means that the value of G will be less than 0. As you can see, it is less than minus 17 kilojoule per mole at 25 degrees Celsius. So in other words, this reaction, it has a strong tendency to form the product. But if the value of K, it is less than 1, so if it is less than 1, it means the value of G, it must be greater than 17. So this reaction will remain mostly unchanged for the product. But we also have the instance whereby the value of G is between minus 17 to 17 kilojoule per mole at 25 degrees Celsius. So this kind of a reaction will have a significant concentration for both the reactant as well as the product. So this is the last slide. And for this last slide, I've promised you that I'm going to remind you about Kc as well as even Kp. So if you're having a hypothetical reaction, A plus B, and the product is C plus D. How to calculate the equilibrium constant? To calculate the equilibrium constant is equals to the multiple of the product divided by the multiple of the reactant raised to the coefficient. So for this reaction, as you can see, C plus D, that the product multiple of the product, we say C multiplied by D raised to the coefficient, and the coefficient is C plus D. This is how to calculate the equilibrium constant. But if your reactants, they are given in terms of the partial pressures, so we are still going to calculate it the way we are calculating the equilibrium constant. But in this case, we are going to term it KP. So there is also the relationship between the value of KC as well as the value of KP. So these two things, in most cases, they are not equal. So if you have KC, you can be able to calculate KP. And even if you have KP, you can also be able to calculate KC. The equation is given as KP is equals to KC RT multiplied by delta N. So in most cases, so when you are given perhaps a statement, of course you'll be given the value of KC or you'll be given the value of KP. So if you are calculating the other one, the only thing that you have to take note of, it will be the temperature as well as delta N. Because R, we know that R, it is a gas constant, and temperature, it should be in the Kelvin. So to calculate delta N, to calculate delta N, you look at your coefficient. It means that delta N, it will be the total number of moles for the products minus the total number of moles for the reactants. I think during the previous lecture, we also spoke a little bit about delta N. So with this slide, ladies and gentlemen, I think we are done with the chapter that was mostly related with the equilibrium, constant, reaction, and all this stuff. So I'm going to post an assignment in a day or two, related to lecture 1, lecture 2, as well as lecture 3. So the date when are we going to write our first official test? I think I'm going to relate that information with you, perhaps via the WhatsApp or remotely, but after we reopen for this short recess of Easter. Thank you, ladies and gentlemen, for listening.